Okay, folks, good morning. Today we are going to study very important algorithm, which is the key exchange algorithm. And now, till now, we were in symmetric key setting. Okay, wherein Alice and Bob share a private key to each other. And that was assumption all throughout, right? Okay, and Mallory or Eve in between don't have access to that key. Now the question that we can ask ourselves, how is that possible? Because it's not it's not between Alice and Bob who know each other and can communicate over some other mechanism, WhatsApp or phone, this key. But it can be, you are communicating with server that is in US or Europe or somewhere or within India. Then how do you communicate that key, secret key, or your machine communicates with that server, the secret key, because it's again through internet, right? So this problem we are going to solve today. Okay, and all this technology this comes under asymmetric key technologies. It's not very old. It's about 30 years or 25 to 30 years back people have devised these methods. Okay, these are the references. You can use any one of these. I will strongly recommend to go through video lectures of Professor Parr. Okay, all right. Okay, so this is we are in cryptographic roadmap. Okay, we have already covered symmetric key part, one-time pad, various ciphers, AES, DES, modes of operation. Then that was it around confidentiality. Then integrity and authentication, we have studied MAC, especially HMAC. Okay, we have also studied hash functions, pseudo random number generator. Okay, we have also covered password management. Now we are into asymmetric part or public key exchanges part, right? We call it asymmetric key encryption, right? So, or we also keep public key encryption. And first one we want to study is how to generate the key, shared key over internet. Okay, all right. So this problem we know already, and then we have all throughout we have assumed that Alice and Bob are communicating to each other over insecure channel, right, or leaky channel or internet. Internet does not give you any kind of guarantee about security. You have to do everything end to end. You can not even assume that routers are reliable. You cannot assume that these ISPs are not looking at your mail contents or whatever you are sending over it, right? So you have to assume it's all unreliable and insecure mechanism. Now we assumed that the Alice and Bob have a same key which Alice uses for encryption. Okay, she uses key K to encrypt message M, gets ciphertext C. That ciphertext C is received by Bob and then uses decryption algorithm and uses same key K over C and gets back message M. The assumption is that both of them have the same key. Okay, now earlier, just about 50 years back, it was actually by physical mechanism. Actually on letter, one city to another city, these key were sent between two units of say army or defense forces, and then actually it is written typed. Keys are typed and then exchanged. Now that's not possible today. And imagine, if it's question of Alice and Bob, they can still find some way, but there can be thousands of people or 10,000s of people, right? Suppose imagine, Amazon server and then everybody else. Look at the number of combination it can be, right? Or within an organization, let's assume 10,000 people are there. Like companies like IBM has, about 200,000 people or 300,000 people, and they want to communicate securely to each other, it means that you have to have order n square number of keys. Okay, so we have seen that these are the problems, key generation problem. Okay, all right, so now simple algorithm is as follows. So we have seen there are two basic issues. First issue is that how to communicate keys securely, the shared key, this is secret key. That's first thing. And secondly, how to reduce or how to generate keys and share when number of people, this n is large. It means that the static mechanisms, like, I mean, if there are n employees in an organization, then everyone has to talk to each other, is a fully connected graph, and you will see that it's order n square, which is very high, right? So for 100 employees, it will be 100 into 99 divided by 2 possible exchanges will be there, which is quite high. Okay, so first thing we need to solve is that how to exchange the keys reliably over insecure medium. Now the first basic thing about this is that both Alice and Bob generate a private key and a public key. So basically Alice generates a private key and public key. So Alice generates two keys, private, which we call as SK, secret key Alice, and PK, public key Alice. Similarly, Bob does too, generates two, SK Bob and PK Bob. As the name suggests, secret key or private key, it means that only Alice, for example, SK, Alice generates private key, means that only Alice will know about it. It is absolutely secret, only or known only to Alice. Similarly, Bob's key is private key is only known to Bob. That's the first step. They both generate this independently. Okay, second is that because you know what we are going to do is absolutely magic. So you'll have to be very careful. Please be attentive. And then Alice and Bob send their respective public key to each other. Because this sounds correctly, you know, that is a public key. It means that everyone should know, every public or Janta should know it, right? So they just send it over channel. Okay, or they publish it on the websites, everyone can see it. Okay, and download it. Okay. Now here assumption is that public key is reaching correctly to other end, and there are mechanism for that. Okay, we'll see some of those, right? But we can question this. So let's assume that public key is reaching to everyone who wants to use this mechanism, and you know, as it is, right, without any modification by Mallory. Now what Alice does is that Alice then uses Bob's public key, which she has received correctly, and her own private key to compute a shared secret. Okay, similarly, Bob uses Alice's public key and his own private key to obtain shared secret. How is it possible? See, Alice and Bob have not seen each other so far. They are not coordinating, right? Or they are independently generating two keys. Each one is and then exchanging public key, and then they are able to come up with shared secret. It's like your machine is communicating to Amazon.com. You don't know where the Amazon.com is. And there you can't privately talk to Amazon.com and then share, you know, or do something. Okay. So pictorially we can see Alice, here is Alice, is Bob. Alice generates private key and public key. Similarly, Bob generates private key and public key. Okay. Now Alice uses, Bob sends public key to Alice, and Alice uses this public key along with her own private key to generate a shared secret. Similarly, Bob receives Alice's public key, uses his own private key to generate shared secret, and you can see there is an equal sign, means that both this whatever they generate is the same. Shared secret is the same. Now, what can you change? I mean, can you think of something? Think of your friend and both of you come up with the same key by exchanging something, and these things are generated independently. Alice's public key will have no relationship with Bob's public key. Can you think? Okay. I will come up with the mechanism, right? Now, in between, Mallory is there, and Mallory can see public key of Alice as well as Bob, and she can't do anything. She can't generate shared secret because she does not have a corresponding private keys of either Alice or Bob. Okay, so now before going into actual theory or this algorithm in detail, let's look at some mathematics. So now it requires a lot of mathematics. Now asymmetric key encryption is very interesting. Is the most interesting part of crypto, but it requires, it's totally based on mathematics. Okay, so now we don't have, if you do crypto codes, then all this you can, this can be covered, but unfortunately we don't have time, otherwise like 4 or 5 lectures. Okay, and also not really part of this course. So we will just assume it as it is, and I will request you to go through any book, especially a paper that I have is there. I think you can read the paper. I'm sorry, not here. In the next lecture I will give you the paper, but here this book you can read. That is Professor Parr's book. Is excellent book. Okay, all right. Let's go back. So now so what we do here, what we use here in cryptography, especially asymmetric key encryption, is one-way function. One-way function we already studied in case of hash, right? So here we'll use different kind of one-way function. One-way function is function wherein if you can given value of x, you can very easily compute value of y. So given x, this is one-way function f. From this you can easily compute y. When you say easily, is computationally easily. Okay, but given you y, now the reverse problem is given you y, can you get from this x? Is infeasible, computationally infeasible, right? So basically you'll have to is f inverse x. So this f inverse cannot be done in reasonable time. Maybe less than 10,000 years you cannot do it. Then we say is infeasible, right? From today's computers. All right. Okay. So now there are two sets of problem two kind of mathematics, two ways of or two different sets of algorithms that we use, and these are based on discrete logarithmic schemes, and second is called integer factorization problem. You would have heard very popular algorithm called RSA, right? That's based on integer factorization scheme that we'll cover in the possibly next class or next to next class possibly. Okay, and there's a company also started by these folks called RSA systems or networks, something like that, and that I think it got acquired by some other company. Okay, now we'll start with Diffie-Hellman exchange. We'll then study in brief Elgamal encryption, which is based on Diffie-Hellman, and then we'll study RSA. Now we need to understand that both of these requires knowledge of modular arithmetic. Okay, or group theory. Did you study this in your mathematics course? Then we can skip this discussion. Did you study this concept? I'm asking you folks, please answer quickly.
Yes, sir.
Yes or no?
No, sir.
Okay, all right. So let's quickly, in 10 minutes, let's cover it. And it's very simple. All I require is that please go through Professor Parr's book or any other book on crypto and you'll understand it, or even mathematics books. We all understand numbers, right? Like integer numbers, not the real number, right? You would have in Python programming, integer numbers are like 0, 1, 2, etc., right? 3, or you can go also -1, -2, and so on. These are our integer numbers, right? Or these are discrete. It means that they are not, there's not continuous. You can't have 1.001, 1.002, and so on. They are discrete numbers, right? Now, second thing is that we do in modular is a finite. Even these numbers that we are taking, set of numbers, we are going to take a set of numbers, right, which is finite. So you say that I will take 1, 2, 3, 4 up to say 12 or 11 or 12, whatever, right? And then after that you won't have any other number. You can't have 13. Then you come back to 1. Okay. So for example here, okay, so you have 1 to 12 numbers, right? Okay, and then you don't have 13, then it repeats. Do you know what is this? We are using this, right, in daily life. What is this?
Mod.
Pardon? Clock, right? We use this kind of numbers, right? I mean, we don't have a number more than 12. If you have traditional clock, then you don't, or maybe up to 24 if you use, airlines clock or whatever, right? So 1 to 12. And if I tell you now that we are having class at 9 o'clock and tomorrow I will take class 26 hours from now or 14 hours from now or 26 hours from now. So what will be the time? 11 o'clock, right? Okay. So these numbers repeat. So we can always calculate that because it simplifies our life, right? Okay. So now we can have this modulo number up to 12, for example, here, because normal clock wraps around 12. So 12 becomes 0. So here is 12. 12 becomes 0, then 1, 2, 3, and so on and so forth. And this is modulo 6. So we'll have 1, 2, 3, 4, 5. And then, sorry, modulo 5, not modulo 6. And then 5 becomes 0 and so on, right? Okay. Now this algorithm, the first one that we'll study and the subsequent one also, is based on group which comprised of strictly positive integers like 1, 2, 3 up to p minus 1, where p is a prime number and 1 is identity element. Okay. So 1 to p minus 1 numbers we use, and p is prime, and you know what prime is. Okay, and this is very large. Large, it means number of bits here in P could be 10, 24 bits. It means that 2 raised to power 24 could be minus 1 will be the highest number here. It's very, very large number. Okay. Okay, so P is very large prime. And then we can see that once we have decided modular numbers, then we can have all kinds of operations, modular, multiplication, addition, and so on and so forth, right? Like we have done addition. When I say I will have class after 26 hours, then you can easily find out that it's at 11 o'clock, right? Okay. Prime number, I'm sure all of us know, right? Okay, so very simple arithmetic we can do now. Okay, we can do arithmetic as long as the results are within that set, right? So say for example, if we decide on these 9 numbers 0 to 8, the results are always going to be less than 9. For example, 2 times 3 is 6, which is right. 4 plus 4 is 8. How about 8 plus 4 is 12? Okay. And if you use only 9 numbers, okay, then result is actually 3 o'clock. Oh, sorry, 3 answer will be 3 because it will repeat after 9. Okay, so we can write this as reminder is 3. So what we can do is that, say, let's take 8 plus 4 is equal to 12, and we have number up to 9, so we can say is a 12 mod 9, which will now if you could divide 12 by 9, we'll get remainder of 3. So we can write this as a equivalence. Here this symbol represent equivalence or congruence. So we can say is 12 is congruent to or equivalent to 9, sorry, 3 mod 9. Okay, get it? Okay, so there are a lot of examples that are given in the book, so you please read through that. And then since a group theory, it will have to follow certain number of rules and will have certain number of properties. So there are properties like closure, associativity, identity element, and inverse element. So pictorially we can, so note that numbers will remain within the range. For example, this is the range, like as we have seen 0 to 12. Okay, 12 is the modulo number, so 0 to 11, so total of 12 elements. Then all calculations that we do, it will be within that. So for example, if you do a here, this is a set of numbers, and if there are two elements a and b, if you multiply that, then this multiplication will also remain in the same set. For example, in case of clock, you do 4 into 4, that's equal to 16. You do mod 12, so that becomes, that's equivalent to, you can say, 4 mod 12. Okay, so associativity is that if you do a multiplied b into c, first you multiply b into c and multiply with a, which is equivalent to you multiply a into b and multiplied with c. So this is associative property also, it follows. Then there is always a identity element, which is 1, such that you multiply this with any other element, it remains the same. And then there is inverse. Now note that the inverse thing is very important, we are going to use it. So basically, if you multiply a with a inverse, then answer is 1. But how do you calculate a inverse is a challenge in this kind of numbers. We will see that. Okay. So please go through this. Okay. So anyway, I mean, let's quickly look at the modulo definition. So modulo operation, we say there are, okay, let there be 3 integers a, r, and m, which is part of a set z or z, and where m is greater than 0, then we can write a is equivalent to r mod m if what? A minus r is divided by m, or m divides, or we normally show this as this one, divides a minus r. Okay, so here what we say is that r is a remainder. If you take a and divide it by m, then r is remainder. Okay, all right. So we can write, in fact, a is not here equivalence, but equal to q times m plus r, where q is, you can always find out, right? But q is usually not important for us. What is important is m and r. Okay, so look at all these examples. A is equal to 12, m is 9, then we can write 12 is 1 into 9 plus 3. Okay, so we can write 12 is equivalent to 3 mod 9. Okay, all right, and so on. Okay, so please go through the same thing we had shown here. So we can write this as A is equal to Q times M plus R, or in other words we can say A is equivalent to R mod M. Okay, all right. Okay, now we will note that remainder is not unique, because if you have a number of ways of getting remainder, okay, remainder may not always be unique. For example, here 12 is equal to, if you divide 12 by 9, you get 3. Okay, now can we also write 12 is equivalent to 21 mod 9, so can 21 be remainder? So if you use this definition, whether M, which is equal to 9, divides 20 minus 1, 12 minus 21, then it's correct, right? So here 12 minus 21 is what? Minus 9. 9 divides minus 9, which is minus 1, right? So it means that 21 can also be written here. Similarly, minus 6 can be written here. Okay. And all these numbers 3, 21, 6 and so on are called equivalence class for this set, and for given a modulo M, and they behave equivalently. So for in this example where modulo is 9, then all elements in this class, this is a very large, this is infinite set, you can go to either side, these are the numbers in that set. Okay, all right. So now why we use this property? Because it simplifies our calculation. Okay, because each element in a class, this class behaves equivalently. Okay. I know I'm going very fast, but please go through this and then when you have time, and then please try to understand it, otherwise refer book. So now something that's very important, the core operation we do in this kind of logarithm is x raised power e mod m, where x, e and m, very large number, which is 2048 bits each. So it means that x could be very, very large, 2048 bits, right? It's very large number. Similarly, e is very large. It could be similarly 2k number of bits. Okay, so multiplication is going to be very, very large. Sorry, it's power. So x raised power e is going to be very, very large. Okay, so whole computation is going to take lot of time. So but using this modular method, we can simplify this, right? For example, you want to calculate 3 raised power 8 mod 7, then we can write 3 raised power, simple method, first method that we do with our knowledge, basic knowledge is 3 raised power 8 is equal to 6561. Then we will find out, we divide this by 7, so we'll get 937, then remainder is 2, then we can write this as 2 mod 7. But this calculation is very, very long, because you will get very large intermediate number like 6561. So we can split this as a 3 raised power 8 is equal to 3 raised power 4 into 3 raised power 4 is equal to 81 into 81, and 81 can be written as 11.7 plus 4, basically 4 mod 7 it can be written as, right? Okay, so basically you have 4 into 4 mod 7, that's a 16 mod 7, and you'll get answer 2. So it's very simple. So by modular mathematics we simplify operation, that's the reason we use it. Similarly, we do division, modular division. Okay, so if we have b by a, so we can write b into a inverse. Okay, mod m. So what is inverse? Inverse is a number we defined as where a into a inverse is equivalent to 1 mod m. Okay, so given A, you'll have to find out A inverse such that you multiply this to given value of m, you get answer 1 or remainder is 1. Okay, all right. Please go through the slides again by yourself. So we have 5 by 7 mod 9. How do you calculate this? Now you will have to, it means that get 5 into 7 inverse mod 9, right? So you'll have to get 7 inverse. Okay, now you'll have to replace this with a number. When you multiply it by 5 will give you answer 1. So now this 7 inverse, if you take value of say what value 4, just a minute. Okay, wow. So 5 by 7 mod 9. So we have to find out inverse of 7. 7 mod 9, inverse of 7 mod 9, which is 4, since 7 into 4 is equal to 28 is equal to 1 mod 9. Okay, got it? Okay. So A into A inverse is equal to 1. That you'll have to remember. And A inverse you'll have to calculate using this method. Okay. So 7. So we'll have to get 7 inverse mod 9 again. Should be, it should give is equal to, it should give you 1 mod 9. So 7 inverse then, oh sorry, A into A inverse. So basically 7 into 7 inverse should give you 1 equivalent to 1. So 7 inverse would become then 4. So 7 into 4, 28 mod 9. Mod 9 will give you 1. Okay, please go through. It's a little tricky, but now the question is that now we are struggling here itself to calculate A inverse. How will computer do it then? So there must be some method, and that method is called Euclidean algorithm. Okay, so I'm not going to go through this. First thing you'll have to find out whether there is an inverse of A available or not. Okay, so now we can say that inverse exists if greatest common denominator for A and M is 1. So GCD of A and M is 1, then there must be, or it means that A and M are relative prime, then A inverse exists. Okay, it means that now all the calculation we are going to do, or algorithm we are going to design, we'll have to be careful whether A inverse exists or not. So we'll have to choose only those numbers where A inverse exists. Okay, so for example, we'll have to find out whether inverse of 15 exists in Z26. Okay, here A is 15 and M is 26. So GCD of 15 and 26 is 1. It means that inverse of 15 must exist. What is it that you can calculate? Okay, and one method of calculating is through Fermat's little theorem. Okay, so given A is an integer and P is a prime, then we can calculate A inverse as A raised power P minus 2 mod M. Okay, this is it will take some time for you to get into it, but unfortunately I cannot spend more than this, right? Already I have covered, taken a lot of time going through it. Okay, all right. So please go through the book. It's not that difficult. Now let's come to Diffie-Hellman exchange, key exchange, right? So we know the key distribution problem. We know number of key problem, right? Number of keys order n square. If number of people who are exchanging keys n is large, Everyone has to exchange key with each other and it could be very large. And of course, you know, Alice and Bob can fool each other. It means that there is no non-repetition. All right. So these are the symmetric tree issues that we have seen. Okay. But symmetric key is very fast. Only advantage of symmetric key first is of course confidential and very fast, and of course one way and one-to-one mapping, right? Something that you're encrypting you can decrypt. All right. But key distribution problem remains, and that we are going to solve with Diffie-Hellman. Okay, and this defines new direction in cryptography. Okay, so what happens is that through Diffie-Hellman we get keys, both Alice and Bob generate key and use it only for short time. Okay, and this reason we call them a session key. We also call them ephemeral or short life key. All right, and then this algorithm is very important, and we are going to use this in protocol like SSH, TLS. TLS we use very often, right? HTTPS uses TLS internally, and IPsec. Okay, look at this diagram, and this defines Diffie-Hellman algorithm. What do you see here? Okay, this is beautiful. I mean, just beautiful. Alice and Bob decides on common paint. And these are the different paints, okay, and they're kept in transparent glass, for example, and they decide a common paint. Now this common paint is known to everyone and nobody can cheat around. It's all published. We say yellow is the common paint color. Okay, so both start with a common paint color, and then Alice decide, here we call it red for in this example. Of course, I mean, when we come to next slide, then we'll colors are different. So she uses a red color here and uses this color, what we call as magenta, or what, I don't know what is this color, maybe light blue or green, for example. Okay, this color is private to Bob, and this red color is private to Alice. Okay, they decide separately, independently. Okay, then they mix this and they get this kind of color, the kind of orangish color. This guy get kind of blue color, and which they send to each other. Okay, so Bob receives this paint color, and Alice receives Bob's color. In between, there's Mallory. Mallory also receives them, but Mallory cannot split these two colors and cannot find out a secret color. So if Mallory receives, for example, this orange color, orange, this one, and then she cannot come to know that she knows the yellow, although she knows the yellow, but she cannot get this secret color out of it. Okay, because number of colors can be very, very large, and there is no direct way of finding out what would be the secret color. Okay, now once Alice receives this color from Bob, she adds to that her private color, which is red, and she gets this color here, which is kind of brown. Similarly, Bob receives this color, orangish color, from Alice, adds to that his own private color, and gets this color, and then both of them have same color. Understood? No? Okay, please go through the slide set of your own. So now algorithmically we can say Alice and Bob want secret paint color, but Alice can see paint colors, but Eve can see, Eve or Mallory, anybody can see the color sent by Alice and Bob. Okay, Alice generates her secret color amber, which is A. Bob generates secret color, which is blue, B. Obviously, A is secret to Alice and B is secret to Bob. And then Alice and Bob agree on common color green. They may publish it, or they may send each other, right? Send it to each other. Now, all this is known to everyone, for example, and they both mix their secret color with G. So what Alice will get after mixing G with her color A amber, she will get green amber, which is this color. Okay, Bob mixes blue with common color green or public color green and gets green blue, this color. And Alice sends GA to Bob and Bob sends GB to Alice. Okay, Eve of course knows G and GB and it's hard for her to segregate or separate colors. Now Alice has received GB from Bob and then she mixes into it A, her own color, and she gets green, amber, blue, GAB. Bob receives GA color from Alice and adds to that his own private color B and gets GAB. So note that both GAB are the same. And Eve cannot generate because Eve gets GA and GB and she also knows G. From that all this she can get is GA into GB, not GAB. This is not as GAB. Okay, so let's move now. Okay, so one-way function we have already studied. Now here something that's important is called this function gx mod p. Okay, where x is very large, p is very large prime, g is specially chosen generator which is known to everyone, which is also large, and x is also very large. Okay, so remember this g raised power x mod p. Now both of Alice and Bob have to calculate this. Okay, all right. So now we know that Alice has two colors, private and public, like two colors that we have seen. Since Bob is also having two colors, private and public. Okay, now Alice has a key A as private one, and then she generates from this a public key capital A, which is equivalent to G raised power A mod P. Okay, note that G is known to everyone and P is also known to everyone. What is secret here is only A. Similarly, Bob has private key B and from this generates, so he's a B, and from this generates public key capital B, which is equal to G raised power B mod P. Note again G and P are known to everyone. Only thing that is he does is he uses his private key to calculate G raised power mod P. Now this A and B they can publish or send to each other. This is known to everyone. Now here this mathematics is that given A, for example, which is G raised power A mod P, if someone receives this number, from this the person cannot calculate A. Okay, that's the theory. Okay, all right, what will happen now? They communicate to each other these colors, Alice and Bob. So Alice can come. Okay, now Alice can compute using her private key A. Alice has received B, Bob's color, multiply or exponentiate it with A. So she will get B raised power A mod P, which is nothing but G raised power B raised power A mod P, which is nothing but G raised power AB mod P. So she generates this G raised power AB mod P. Similarly, Bob receives A from Alice, which is nothing but G raised power A, exponentiate it with B, so it becomes G raised power A raised power B, which is nothing but G raised power AB mod P, which is same as the one which Alice has generated. So this is the shared key now. Okay, are you able to understand? There is a trick. Trick is here that given A and B, of course, Alice and Bob can generate adding private key to this, a shared key, but given A and B to anybody, they cannot find out small a and small b. Okay, which is private key to A, B is private key to B. So that's the interesting thing. Now, once we have generated this key, shared key S, then of course, we can use it any way we want. We can use in symmetry key setting. All right. Note that P is very large prime and generator is also very large because it is an element of 2 up to P minus 2. It could be anything. The P is very large. That's important condition. It's very large and prime. Okay. So this problem, discrete log problem, is that given this public key G raised power A mod P, which belongs to Alice, and nobody can find out A. All right. But for that, A and B also have got to be very large. Okay. So we can define this problem as follows, that given G, P, G raised power A mod P and G raised power mod P, there is no polynomial time attacker can distinguish between random value R and G raised power AB mod P. Okay, so we'll skip this. Okay, and we'll jump on to the, please go through this. It's very same thing that we have discussed. Okay, another 2 minutes, 2-3 minutes will close. So this is a process pictorially shown. Alice generates A, secret key A. Bob generates secret key B. Okay, the first step. Alice calculates public key from private key, which is G raised power A mod P. Notice that G and P are public. Everyone knows it. Alice, Bob, and Eve also knows it. But Alice calculates G raised power A mod P and send this number that she has got to Bob. Bob receives G raised power A mod P and uses his own private key by calculating G raised power A raised power B, which becomes mod P, which becomes G raised power AB mod P. Similarly, Alice receives Bob's public key, which is G raised power B mod P, uses her own key A here and gets G raised power A mod P. Okay, so both of them now have same key. Okay, all right. All right, so now note that we can use this only for short period of time. And there is something called forward secrecy, right? I mean, so after use, I mean, when Alice and Bob have calculated this key, they have to after the communication is over, they have discarded it. And somebody hacks into their machine. Since there is no private key available, only public key is visible to Mallory, or she has stored it somewhere, she cannot find out. She cannot do anything about it, right? Once Alice and Bob discards this A, B, and K. All right. So let's look at example. It will become little clear to you. So P, and note that P and G are public knowledge. So Alice and Bob agree on P is equal to 23 and G is equal to 5. This is known even to Eve. Okay. Now Alice chooses A is equal to 6. That's her private key, and then calculates from that. Okay. G raised power A mod P, which is 5 raised power 6 mod 23. If we calculate this, comes out to be 8. Okay. Bob independently chooses this key B is equal to 50. Note that there is no correlation between A and B. And then calculate this 5 raised to power 15, which is G is 5. So 5 raised to power 15 mod P is equal to 19. Now you are going to do logarithmic, modular arithmetic to reduce this problem, right? That's the reason we use modular. So he gets public key as 19. Okay. Now he sends this 19 to Alice. So Alice gets this public key here, uses her own private key, which is 6. So it becomes 9. And she calculates secret using 19 raised to power 6 mod 23, which is 2. Bob receives 8, which is Alice's public key, uses his private key 15 and does this calculation, which is 8 raised to power 15 mod 23, answers is 2. So now 2 becomes a shared secret. Okay. So in practice, now we have taken here P is 23, we cannot take this, right? Otherwise it's easy to break. P will look something like this. This of course hex shown in hex, yeah. Okay. And similarly, G we can do anything, say 2, but both private and public keys are then, that's A and B are must also be 2048, means that A and B will also look like something like this. Please go through another example here and it will become clear to you, right? All right. Okay, any question? Please go through this PPT before we have a class today at 7. Okay. All right. Thank you.